you all. We start our second lecture today. We are starting. So, let me remind you where we have left thermodynamics. It was on Sunday. So what we have managed to prove, using a lot of hand-waving arguments, is that there is some sort of a variational principle, which I would say the following, that if I have a system and the system is in its equilibrium state, any fluctuations, okay, so remember, any fluctuations or imposing some sort of an internal constraints will only get the entropy of the system bigger. Okay? So the variational principle that we know so far fluctuations slash internal constraints decrease the entropy of the system. Fluctuations or internal constraints around what? Around the equilibrium state. Okay. Another thing before we continue, so part of you may be wondering that, well, I want to ask a question, but my English is not good enough. So first of all, forget about it. The English of everybody is excellent. But if you're still stressed about your language, you can raise your hand or ask me. You can ask the question in Hebrew. I will translate it into English, okay, and we will continue. I cannot do this with Chinese, I'm sorry. But in Hebrew, if you struggling somehow with the spoken language, okay, just ask me in Hebrew, I will translate the question. All right, so this is where we left. Now, so this variational principle is for the entropy, okay? I have a system, I have equilibrium state, all the different small fluctuations, okay, are only decreasing the entropy. I'm claiming, or what we have claimed last lecture, is fluctuations or internal constraints are exactly the same. Okay? How we claim this? We said the following. So if we have a system, all right, and somehow we imposed an internal constraint, okay, for example, some sort of a separation that separates the system into two parts, and immediately we take out the constraint. Okay? Now this procedure of taking out the constraint is going over a very short temporal time. Okay? Delta t that it took me to take out the constraint is extremely small. The moment the constraint is out, I don't really know how the system got into this state. It got here because I imposed the constraint and slowly brought it over here, or it got here because it performed some sort of a fluctuation around its equilibrium state. It's impossible to discriminate between those two scenarios, right? So for me, fluctuations and internal constraints are exactly the same or almost the same because I cannot discriminate what brought the system into the state. But it's actually very valuable. Why? Because I can use these ideas. I'm imposing a constraint, bringing a system to some additional state, and then claiming that it's actually a fluctuation. Okay? I'm less worried about the internal constraint, but this is much more stronger claim that fluctuations only decrease, as long as the energy is constant, only decrease the entropy. Okay? So this is variational principle number 1. Now what we are going to do is to deduce a variational principle for energy. Okay? How we deduce it? We use almost exactly the same ideas as we used for entropy. So the variational principle for energy goes in the following fashion. Let's assume that I have a system, okay, and the total energy of the system is E. Okay? The total energy of the system is E, and I'm imposing a constraint, okay? I'm imposing a constraint, internal constraint, such that this is E1 and this is E2, and those systems are a little bit separated or somehow separated from each other. Okay? I can tell you the following, that the total energy is E1 plus E2. Okay? The next step that I will do, I will say, well, I'm performing a small fluctuation such that I can, or during imposing some holes inside this constraint or imposing additional constraints, such that part of the energy flows from the right-hand side to the left-hand side. Okay? So what happens over here? I will have E1 plus some delta E, and I will have E2 minus delta E. The total energy stays exactly the same. What happens with the entropy? Okay, the entropy must what? Increase or decrease? Decrease, right. So I do know that the entropy of the system plus the entropy of this system is smaller than the entropy of the total system with energy E1 plus E2. Okay, so S, let's call it S1 of E1 plus delta E plus S2 of E2 minus delta E is smaller or equal, okay, to the entropy of E1 plus E2, which is the entropy or the total entropy of the whole system. So, but it still does not get me anywhere. But then I remember that there is another property of this function, entropy. Entropy is monotonically increasing function of the energy. So there should be some energy, let's call it E prime, that is smaller than E1 plus E2, okay, such that the energy of the first system, E1 plus delta E, plus the entropy of the second system, where it is E2 minus delta E, equals exactly the entropy of the whole system with E prime. Okay? I use this property of monotonicity. Okay? The moment I do this, I can say, well, what happened to the energy? So the system, the entropy in this state, I can say that this is the entropy. I'm keeping it constant. Okay? If I'm keeping the entropy, so what happened over here? This describes to me the entropy when I imposed a constraint. Okay? The entropy has not changed. Okay? I'm basically saying any constraint that I will impose on the total system while keeping the total entropy constant must lead to what? To a decrease in the total energy of the system. Right? Because I do know that E prime is smaller than E1 plus delta E plus E2 minus E delta E. Okay? So imposing a constraint what it brings to us? It increases the total energy of the system. Okay? Now remember what I told you before. I cannot separate between the situation when I imposed a constraint or the system performed some sort of fluctuations. It got there in a random fashion. There was an equilibrium, it fluctuated around the equilibrium, right? And it got into this new state. I don't know if this state was obtained due to the constraint or it was obtained due to the fluctuations. Okay? So I'm getting, again, a variational principle. For energy. So fluctuations or internal constraints increase the energy of the system. So this is now something that maybe you heard before, that the system prefers always to be in its minimal energy. Right? The equilibrium state defined, how? It's defined that the energy of the system reaches its minima, okay? While I'm keeping the entropy constant. Okay? And it's similar to this variational principle, which says when I'm keeping the energy of the system constant, okay, the system will reach an equilibrium state when the entropy is maximal. So maximization of entropy or minimization of energy. It depends what I'm keeping constant. If I'm keeping energy constant, maximal entropy. If I'm keeping entropy constant, minimal energy. Any questions? Yep.
Now understand about the smaller of the input, because as we have thought can exchange energy and the containers of the two boxes.
Mm-hmm.
The energy, the total energy is unchanged.
Yes. No. It's not that the total energy is unchanged. You see, the total entropy is not changed. I've reached this state. I had an argument about that I had exactly the same amount of energy. I reverse the argument over here. I'm saying, look on this situation. Okay? This situation is where I do not have a so this is the energy of the system. This is the situation where there is a constraint. Okay? So no constraint or whatever situation, and a constraint over here. Now you calculate the energy on the left-hand side is greater than the energy of the right-hand side.
Yeah, but how about in the top of the...
This was a different state, right? So I've started that I raised it. I started with a situation that when I had a constant energy, and I let the energy flow, okay? And then I found another state, okay? So this guy, S prime with E prime, I claim the following. This is some intermediate state that has lower energy, okay? Okay? But the entropy is exactly the same.
Oh, so this state is unstable.
No. This
No.
I used the following thing. I write a diagram. I had a state without constraints. Okay? I have a state, another state, where I impose the constraint. The energy was the same energy. And this is a state, okay? And this is the state with a constraint. Now I'm saying I can have additional state with different energy but the entropy is the same. Okay, I started from here. I realized that I can get to another state with the same energy but different entropy. Okay, now I'm taking the entropy of this state with a constraint and I'm claiming that there exists another state with the same entropy but with different energy and it has no constraints whatsoever. Okay, so now I'm looking only on this transition. Okay, so I had a situation. I'm not changing entropy. Okay, I'm adding an internal constraint, and what I see is that the energy is getting lower, higher. Okay, I use this guys in order to create this state, and then I invent an additional state that I know that the entropy should be exactly the same. Okay. All right, so let's use a little bit our variational principles for pretty much very trivial questions. Because usually when thermodynamic laws are defined, they defined as statements about temperature. What we have done, right, we have defined the thermodynamic laws by using the first one in order to define energy, the second one in order to define entropy. Okay? The definition of temperature was based on the behavior of energy and entropy. Right? I haven't said anything about how the temperature behaves. The only thing that I claimed is the temperature is a positive function. Okay? It was defined based on the monotonicity of energy, of entropy with energy. Okay, so let's look what happens if we have two systems, E1, okay, S1 and T1, an additional system, E2, S2 and T2, and we let the heat flow from one system to another, and we say what when we're looking on these systems coupled together thermally now, okay, no heat can escape of this system to the outside world, only the heat can be exchanged between those two systems. Okay, and I'm asking now the question, what is the relation of the two different temperatures? Okay, how T1 is related to T2? We all know the answer. If you take two systems together, you bring them into a thermal contact, okay, you apply adiabatic constraints on the outside, eventually the temperatures, okay, must be exactly the same of the two systems. So let's see how we obtain this from our variational principles. Okay. So, yep.
קודם מתחיל מילוצים ואז יוסיר אותה ומגיע לשיווי משקל, כאילו הגיוני, נגיד בחוק השני של התרמודינמיקה זה קצת יותר מסתכל.
Okay, so the question is, what is, let me rephrase it. The question is, what is more convenient, okay, to start with the constraints and then, so actually I haven't understood your question. עוד פעם.
לא היה יותר נכון להתחיל מאילוצים ואז להוריד אותם ולומר שהאנטרופיה גדלה או שהאנרגיה קטנה, כי אתה בעצם אמרת את כל זה הפוך, אנחנו יודעים שהמערכות בדרך כלל שואפות לשיווי משקל, לא היה יותר נכון להציג את זה אחרת?
So the question is, shouldn't I start with derivations of internal constraints, applications of internal constraints, and using some properties of equilibrium instead of making statements about entropy, something like that? Well, the answer is no. Okay, and why no? Thermodynamic laws, as I presented them to you, are not the same, or were not phrased in the same fashion in the 19th century. Okay? What the two laws that I stated over here are basically based on observations and the concept of entropy that were invented afterwards. Now, about the constraints, I need this trick, okay, in order to apply the laws and say something about maximization or minimization of the entropy or the energy. I cannot start with the statement that, well, the energy must reach its minima, or the entropy must reach its maxima. Okay? What you're proposing is, let's start with this statement and we'll obtain everything else afterwards. Okay? I think I could do this, right? I could do this, but it's actually less convenient. It's much less convenient to start with a variational principle without actually relating it to some sort of observational facts. And the first fact is the conservation of energy. It's very clear. The second fact is concerned what is entropy. Okay? Otherwise, I should, I need to explain to you what is entropy before, okay, I'm starting to say that the entropy must be maximal. So the two thermodynamic laws that I stated, they're even simpler than the statement of maximization or minimization. Any further questions? No. Okay, so here we are coupling those T1 and T2. And we want to see what happens. So what approach should I take? The approach, as it's usual in physics, it's approach of perturbation. I'm looking on this system, okay? All this approach of imposing internal constraints. It's an approach of perturbations. I'm taking the system, I'm changing something small inside the system, and then I'm looking how the system responds. I'm looking on the response and I'm trying to understand what actually happens inside. So what I'm doing here, I'm saying, let's impose some sort of internal constraint, okay? And when I'm imposing some sort of internal constraint on the system, I know that the total entropy, okay, of the system must be smaller than 0. Why? Because I have this variational principle that states, so this is the energy, that states that in equilibrium, okay, the entropy is maximal. So when I perturb the system, it fluctuates, or I impose a constraint, the entropy goes down. Okay? So if the entropy goes down, I know there might be some sort of an exchange of energies between those two systems. Right? But the energy cannot escape to the other outside world. So delta E1 equals minus delta E2. Okay. There is only exchange of energies between those two systems, heat flow, for example, and no flow of heat outside. Okay. So let's see what happens. We state the following. The total entropy is S1 plus S2. Right? This is very simple because entropy is an extensive property. The total change of the entropy, okay? The total change of the entropy is the change of the entropy of system number 1 plus the change of the entropy of system number 2. Okay? But what have changed? So this guy, I can say, this is delta S1 to delta E1, delta E1, okay? I Taylor expand the change, and delta S2 is delta S2, delta E2, delta E2. Okay? This is a partial derivative of how the entropy of the system number 1 changes with the energy, and this is the partial derivative of the entropy of system number 2, how it changed with the energy. What is ds dE? 1 over T. Okay? So what we have over here is 1 over T1 delta E1 plus 1 over T2 delta E2. Okay. This equals, because I know that delta E1 equals minus delta E2, 1 over T1 minus 1 over T2 delta E1. Okay. And I know what I know. The entropy must go down. Okay. Okay, this is a bold statement, but this guy is actually arbitrary. It can be positive, it can be negative, it can be whatever I want. Okay? It depends on the constraint that I impose on the system. I can make it negative, positive, I can make it 0. Okay? But this statement must be always true. Why? Because the entropy is always negative, the decrease. It always decreases. What it means? It means that 1 over T1 minus 1 over T2 equals 0, or T1 equals T2. So the temperatures of two thermocoupled systems must be equal to each other. This is a very trivial fact, but we obtain it by using our variational principle, so not the other way around. If you open a classic book on thermodynamics, you will start that with the fact that the temperatures are equal to each other. Okay? What we have done, we started with the fact of some words about entropy and how it maximizes, and we obtain exactly the other way, okay, that people usually start with. Equilibration. So when two systems equilibrate, they reach exactly the same temperature. Okay, we can do something else. Okay. We can say, well, let's take two systems with different temperatures, okay, and couple them one to another. Okay, so I have E1 S1 T1. I have E2 S2 T2. Okay. So those two systems were separated. Any question you can ask me? I'm here. Okay. So those two systems were separated. Okay. Now I make a thermal contact between the two systems, and eventually they will reach equilibrium. Okay. What happens on the way to equilibrium? Okay. This was equilibrium number 1. This was equilibrium number 2. Okay, what will happen on the way to equilibrium? Okay, what we know what should happen. There should be a heat of flow. I allow heat to flow from one system to another. So from where to where the heat will flow? It's obvious, from the hot system to the cold system, right? There is no flow of heat from colder systems to hotter systems. Okay, so let's see if this is actually what happens. Okay, so we start with the system. We take out this adiabatic separation. There are adiabatic walls all around this guy. So no heat basically gets out of the system, all right? And then we say the following. So we started with some total energy S1 plus S2, entropy, I'm sorry. During the process, there was a change of entropy for system number 1, there was also some sort of a change in entropy of system number 2. What is the total change in entropy of the both of the systems? Is it positive, negative, equals to 0? Positive. Why it's positive? Yes, because the process is adiabatic. Okay, this is part of the second law of thermodynamics. If I start from situation number A, I reach situation number B in adiabatic fashion, the entropy increases. So this guy is greater than 0. Now I can say, I can use the same trick I've used before, right? What I can say over here, what is delta S1? Is ds1 d1 delta E1, okay? What is this guy over here? It is ds2 delta E2 delta E2, and then we'll have a plus over here, and it's greater than 0. Yep.
So I didn't quite understand the difference between these two examples.
The first example, they were already in thermal equilibrium. The second example, I have taken two systems, the temperatures are different. Okay, they're not in thermal equilibrium. And then I coupled them. Okay, I coupled them and I imposed adiabatic walls around the E1 and E2. What happens to the system? Okay, that's the question.
So in this example, the temperatures were the same even before you put them together?
Well, no, this is what I got. Because I said the following, those two systems are in equilibrium. Okay, remember, I don't know how temperature behaves. Okay, I have to deduce it. We have an intuition about temperatures, but I don't know. Okay, I'm saying if those two systems are in thermal equilibrium, what is the relation between T1 and T2? And what we have obtained that the temperatures are equal to each other. Right? Now I'm starting with a situation that T1 is different than T2. The systems are coupled now, and they somehow reach equilibrium. And now I'm asking of eventually when they will reach equilibrium, T1 must be equal to T2. Okay, you agree with me about that. But what happens on the way? The heat, where it flows from this system to this system, or from this system to this system. Yeah, but let's see it. Okay. Okay, so delta E1 plus delta E2. Yep. Yep. Well, different initial condition. The difference is that this system, when they already reached equilibrium, okay? This system is before they reached equilibrium, okay? I know what will happen at the end. At the end, T1 must be equals T2. But if I've started with different temperatures, okay, if I started with different temperatures, how the process will continue? There will be, we know there must be a flow of heat from one side to another because it cannot get out of the system. Question is where it goes, to the left or to the right? Okay, what we know also, there is no energy that gets out, right? So delta E1 equals minus delta E2. Okay. Then I can say the following. ds1 to dE1 is 1 over T1 delta E1 plus 1 over T2 delta E2 greater than 0. Okay. And I obtain that 1 over T1 minus 1 over T2 delta E1 greater than 0. Previously, delta E1 was completely arbitrary. Okay, I didn't know how those two guys are related. Now I am saying I know how those two guys are related. One is bigger, the other one is smaller. And this will affect delta E1. So the first case is T1 greater than T2. When T1 greater than T2, 1 over T1 is smaller than 1 over T2. So this guy is negative. If this guy is negative, delta E1 is also negative. Delta E1 is smaller. So the heat flows from hot system to the cold system. Right? Very trivial statement, we all know that, but you see, we do not start with those trivial statements. We start with some maximization and minimization principles. Okay? And we basically reach back to something that we all know from high school. All right, we have 4 or 5 minutes left. So let us finish with something different. So what we know so far, we know that the change of energy, okay, that the change of energy is TdS, okay. We will have here minus PdV, okay. And we also have here, if we have composition of only one type of molecules, plus mu dN. Okay? So I have only one type of molecule inside the system. Mu is the chemical potential. Chemical potential. It basically states how the energy changes when I add mass to the system. Okay? This is mu. Now, if I look on this equation that we derived in the previous lecture, what we know that E, which is a function of state, depends on what variables? Depends on S, right? It depends on V, and it depends on N. Great. So if I'm coming to an experimentalist and I'm saying to him the following thing, look, you have your gas or whatever system, let's take an experimentalist like Eli Slutskin, right? I'm coming to his lab and I'm asking, look, Eli, your energy depends on the volume, on the number of colloids that you have in your system, and on the entropy. I want you to change the entropy of the system in such and such fashion, okay, in order to change the energy. The experimentalist will look on me and say, forget about it, I don't know how to change entropy. I can change pressure, I can change maybe temperature, I can change a lot of things. Entropy, I don't know what it is. How am I going to change it, right? So we are encountering some sort of a problem that we have variables, or at least so far we have variables, that sometimes we cannot control in an experimental lab. So it's easy to do everything on the board, right? I can have this variable, that variable, but eventually, an experiment, I have this equipment, and this equipment can control volume, molar composition. It has nothing to do with the entropy. Okay? So the question is, can I invent some theoretical framework in order to control or define function of state, okay, that will be dependent on different variables? Okay? What I want to do is basically describe to you a technique that will take me from, for example, energy that is a function of entropy, volume, and N, to something that I can have control over, okay? Some sort of a function, let's call it A, that will be a function of temperature, volume, and the molar composition. Okay? What is this technique called? It is the Legendre Transform. Okay? The whole point of this Legendre transform is how to change variables over functions of state. Okay? What the Legendre transform looks like and what it tells us. So let's assume that we have a function of x1 till xn. Okay? This is our function. I'm saying that the differential of f is what? Is a sum from I goes from 1 to n, okay, of ui dxi, where ui is df to dxi are simply the partial derivatives, where all the other x's are taking constant. Right? Very simple. Now let's define g, which is what? Which is simply f minus I goes from r plus 1 till n of ui xi. This transformation over here is called the Legendre transformation. What am I achieving by performing this simple shift? Okay, let's look on the differential of g. What is d of g? So d of g is d of f minus d of all those guys that I have on the right hand side, r plus 1 and ui xi. So df, it's a sum of from 1 to n of ui dxi. Right? This is df. We know this from here. What we have over here is minus a sum from r, from I equals r plus 1 till n of ui dxi, okay, and what is the other function? Minus, or I'm sorry, plus xi dui. Okay. What it means? It means that what we left with, I goes from 1 till r of ui dxi, okay, and on the right hand side over here, we're left with plus sum from I equals r plus 1 till n of minus xi dui. This is d of g. What it means, what are the natural variables of g? R, x1, x2, xr, okay, ur plus 1, ur plus 2, u of n. Okay? So by performing this simple transformation over here, I have additional or another function, g, okay, that have different variables right now. The same thing I can perform with energy. Okay? What we will see in the next lecture, that I can actually obtain additional functions of state by using this Legendre transformation. Okay? And what I will obtain is, for example, A is a transformation that I am subtracting from E minus ds. What it gives me, so E was a function of S, V, and N. T is dE to ds, right? Okay, so what I've got over here is that A is a function of t, v, and n. This is the Helmholtz free energy. Okay. I can subtract something else. For example, I can subtract from E ds, and also I can subtract minus p and v. Okay? This g function over here, is a function of what? So I've subtracted minus ts, so instead of s, it is now a function of t. I've also subtracted pv, so instead being a function of v, is a function of p. I haven't changed n. Okay? This is Gibbs free energy. Okay? I can also perform the same trick with E minus PV, E plus PV, for example. This is enthalpy. So those are additional functions of state, and we can use them instead of entropy, or energy, I'm sorry. Okay? And in the next lecture, we'll learn about some properties of these functions and why it's important to perform this Legendre transformation. Thank you.